Welcome back to the story about 4D printing. We have heard about the theory behind it, but today we are digging deeper into the applications. Where can you use these materials and how are they manufactured? That's pretty interesting. So hang on, and Mehrshad will guide us through interesting applications.
Yeah. And then people are saying, but it's very funny, but how can you use it? Where can you use this in the real world? And
Yeah,
this is the Everyday Metallurgy podcast. So we need to relate it to our everyday. So where do we meet these materials, or where can we meet them? Or
yeah,
how will we suffer if they are not there?
yeah. There are many, let's say, NITI based products in the market. So we know they use this NITI, for example, for cardiovascular stents. So this is
Mm,
not something new. Maybe more than 1 or 2 decades is already in the market. We know already they use it for orthodontic, for example, wire, when you want to get a specific U shape of the teeth, and then you can, usually dentists somehow connect it to the deformed teeth, and by
mm,
body temperature, push the teeth to go to the right direction, all the teeth.
yeah.
We know already has been used this one in the, let's say, the wing of the airplane or the actuators, because normally what we have for activation in the actuators most of the time is using the mechanical force externally.
Mm,
But you can imagine we have a material in response to temperature or electricity can be activated, and if be activated, that we
mm,
can get that specific function we are looking for. So the application is already there, but the question is how we can make it, let's say, more common for the variety of applications. Because if we are talking about, for example, nickel titanium in particular, this is
mm,
not very cheap material. So somehow
mm,
the cost is close to the goal. And what
mm.
we can do, we can understand or discover a new type of shape memory materials. And I already know there are lots of group working on that, like iron-based shape memory materials or
It-
copper-based shape memory
yeah.
materials that are
Yeah.
cheaper, somehow similar functionality.
Mm,
Or if we want to have very particular application for that, for example, if you want to, what you mentioned at the beginning of this podcast, high temperature shape memory, then we can add additional element to that. And that element can increase that transformation temperature to 700,000. So that could be
mm.
application like
Wow.
NASA working on that for
Yeah.
time being.
Mm,
Yeah, so there are already lots of application and working on that, but whatever the other researchers are trying to do to facilitate that, come up with the new manufacturing process, developing new type of the material, and provide a better opportunity for designers all around the world using the cheaper and easy to use material for developing the smart products, what they're
mm,
trying to do. Yeah.
yeah. Um, so this designing new materials based on cheaper materials, uh, is it trial and error, or can you use machine learning? Can you calculate thermodynamically the properties of shape memory alloys?
Yeah, definitely. One of very interesting part of this field, if I call it, is about developing a new material. And when you want to develop a new material, specifically new alloys, there are some tools already can help you with that, like thermocal, or you
Mhm.
mentioned nicely about the uh, power of machine learning, how you can combine the different, let's say, elements with the different percentage for the certain
Yeah.
properties or application. So the same thing also can be used for shape memory alloys.
Mm.
We only can consider or should consider additional properties in the end of the day. For example, in our case, super elasticity, shape memory behavior, and stuff like that.
Yeah.
but we still can use them, and we need to use them because otherwise uh, we cannot, let's say, we try and error to just find something. Try and error was, or accident was something this material discovered. But from now
Yeah.
on, we have some tools and we need to
Mhm.
use those tools in
Yeah.
order to develop the materials and make it
Mm.
better.
Yeah. I agree.
Hey, I'm just breaking in because we are talking about potential ways of calculating or simulating instead of running trial and error. And in fact, if we go back some episodes, I had a fantastic interview with Nicholas from Thermocalc. And I will strongly encourage you to take a look at those episodes. There are two. One where we look into equilibrium in liquid state of steel melt, and another one where we look at non-equilibrium in a hardening process, where we are hardening precipitation hardened steel to see if we can predict the hardness and the properties of that, even though we are not in equilibrium. So take a look back at it. It is very interesting, and I learned a lot that day. I'm sure you can learn a lot too.
Uh, I have also sometime been talking to young people about is there a future for metallurgy, or is metallurgy something that was developed in the past? Uh, and I think this field, using the complex understanding of computer science, thermocalc, machine learning, artificial intelligence, and combining that with metallurgy, it's mind blowing what is possible. Do you agree that there are tasks for the young people to take over?
Definitely, definitely. I totally agree with your comments. I'm teaching a course of manufacturing for some years. So one of the things we start for manufacturing is, first of all, we give some insight about the material science, and metallurgy is, of course, a very important part of that.
Mm.
So you need to first understand the basic and the materials, and after that you can apply it. For example, apply a different type of manufacturing process in order to produce a new product. So those knowledge are necessary. And whatever I mentioned about developing a new composition or manufacturing shape memory alloys with a different type of additive manufacturing, they are all related to the basic metallurgy, material science that we need.
Mm.
And we need to understand what is happening in the microstructure of the material. The picture that you have behind of you is not
Yeah.
only for the stainless steel, it's also, we can see a lots of picture, specifically when you have a composition of the different elements in the
Mm.
shape memory. When you have nickel, I don't know, titanium and copper, or with the other type of elements, and you
Mm.
change the microstructure, and based on that, you change the transformation temperature,
Yeah.
functional performance, and in the end of the day, the application of the material. So
Mhm.
we need to know it, and I totally agree with your comment.
Yeah. Mhm. Yeah. So, uh, where do you see the future of shape memory materials, and what role do you and your team play in reaching that?
Yeah, I'm quite happy is being some years lots of attention are on specifically shape memory alloys, and there are a couple of good conferences every year or every 2 years. A lots of researchers all around the world gathers and share some information. Like I said, one field and one, let's say, focus is on material developments. There are uh, some universities and also some companies. They develop business on the topic, and they come every single year and talk about, let's say, the new type of the composition they develop for a specific application. For example, elastocaloric application is something very new and very interesting about the shape memory alloys. It's been like a decade, maybe less. They are talking about shape memory, elastocaloric behavior of the shape memory, and specifically using additive manufacturing to develop kind of application for that. So we need a more, let's say, efficient material for that. And there are some groups and some companies working on that and provide those information for us. Uh, the other part of that, the field I am working on that is additive manufacturing of the shape memory alloys, because like I mentioned earlier, so far, most of the manufacturing processes were limited to conventional manufacturing processes, but additive manufacturing can give us a better opportunity to make very particular and complex part. Imagine instead of the tube, like NITI stand or tube shape I mentioned to you earlier, we print that part and we customize that specifically based on the body dimension of the patient. So instead of making lots of parts with the different sizes, we can just have very specific, let's say, customized part for one patient, which is different with another. The same thing also for the implants. For example, the bone implants is some 3D printing specifically of bone implants is not something new, but what we are trying to do, we are trying to print, let's say, architected structures, because we know if we have architected structure for bone implants, we have possibility to also bone growth, and that is something nice for time being for the patients, that implants could be part of the body. So if we replace that typical materials with shape memory materials, then we have opportunity to have like mechanical properties close to the bone and close to the bone stiffness, and also we can have benefit of the superelasticity behavior. When a heat or something apply on that, it can recover the original shape. And similar things also in the different industries, like in aerospace. We recently started a project to how to use the 3D printing for make like a flexible part for the wing of the airplane, how we can change the shape of the wing in the different temperature. So this is the thing that we are working on that, and I think in the time being would be better, and also thanks to also other groups and other companies. I think during next even 5 years, I would say, we are going to have much nicer and smart products of shape memory materials.
Yeah. Very often the nickel titanium composition is quite narrow in where it works. And when 3D printing, you must be able to make variation in that composition. So to control exact position where you want the shape memory function and another part of the component that is normal.
True.
Is that also a possibility you're looking into?
Yeah, your comment in general was correct, meaning shape memory alloys are very specifically NITI is very sensitive about the percentage of elements. Even, for example, 55 Ni 45 Ti, if you make 55 40 54.8, you have a different transformation temperature and macrostructure compared to other ones. 0.1% can change everything. You don't want that happen. And you can imagine you have one additional challenge, adding additive manufacturing, and you melt the material, and sometimes you evaporate nickel content, and then you have a different microstructure and functionality. So whatever we're trying to do, first of all, find the optimal process parameters to avoid that. Or if we do that, somehow we have a control to be able to just have, let's say, a very nice and controlled process parameters in the end. And then you can also sometimes tune it on purpose. You can increase the Ni evaporation, and then instead of, for example, super elastic material, you can have shape memory effect material, and both of them can be in one component. And then you can make design, like, let's say, a multifunctional actuators or part. And this is something you can benefit of manufacturing processes like 3D printing.
Yeah, that's difficult with the casting process.
Absolutely right.
Yeah. Mm.
Yeah, maybe I can add one thing more on top of that. So one thing that you can do, design of the gradient structure or multifunctional structure in this way. The other way is using, let's say, multi-material printing. So this is what we are already doing also within
Yeah.
some research we are doing.
Mm.
So imagine if you have one product, one side of the products is
Mm.
one type of the shape memory, the other side of the products is another type of shape memory, or no, even another type of the material. If you
Mm.
have nickel titanium combination with, I don't know, titanium alloy or Ti64,
Yeah.
then it could be kind of the application, for example, for medical bone implant, where
Mm.
you want to have a different properties in the different part of your parts.
Yeah.
So this is also something separately you can investigate through the different research. This is what we are already doing also with our researcher in our.
Mm. Yeah. Yeah. So the future is still very open for a lot of investigations.
That's correct.
Yeah. Uh, Mersha, if people are interested to know more, uh, where would you recommend? You said there were conferences. Uh, will you share some links to where they can find more information? And are they also allowed to reach out to you directly?
Definitely, definitely. Feel free to contact me. I am available in LinkedIn, and also my email address is also available on the website of the university. And yes, and the conferences I mentioned, one of them is SMSD, Shape Memory and Superelasticity or Superelastic Materials and Technologies. The other one is ESOMAT and also ISOMAT. There are two different, both of them about martensitic materials. And they are, let's say, two leading conferences at this moment focusing on the shape memory materials, but not limited to them, because I know nowadays lots of other conferences, for example, fully working on the materials or fully working on additive manufacturing. They always
Mm.
have a part or section related to the shape memory or a smart material in general. Yeah,
Yeah. Perfect. Thank you very much. I
no
learned a
problem.
lot, and I think your graph showing the three dimension uh, helped a lot.
Yeah, okay. Happy to hear that.
Yeah. So thank you very much. Enjoy
No
the rest
problem.
of your day.
Thank you.
Bye.
Bye.
Thank you very much for following the episodes on 4D printing or memory shape materials. I learned a lot, and I was pretty amazed of the possibilities you have, or the design, or the come back to the original shape. If you understood everything about the graph Mehrshad showed, you're pretty smart. I still have some difficulties in figuring, even though I told him that I fully understand. But I think this is the purpose of everyday metallurgy. It is sharing, it's being open about things we don't understand, because only if you're open, your curiosity will grow. Therefore, we can share our doubts, we can share our questions, and I absolutely also hope that you will share this episode with your friends in the Material Science Society. So thank you very much for following.